Kirchhoff's rule. So this is one, like that number one, just a little bit nicer. And so here's this situation, 3 batteries, 3 resistors, and so the question we're asking here is what's the current going through the 10 ohm resistor? Okay, so here's the first step, and this is again the step that I think when you're starting out can be the trickiest. And so here I picked a couple different situations of currents. All right, so you guys tell me which one of these pictures would be a valid way of representing these currents here. Okay, so talk with your neighbors and see what you think. That's, again, the first step of a problem like this is breaking it out like that. Okay, so this is, I think I agree with the majority here. So in my method of doing this, basically 2 and 3 are totally fine. So with my method, you've got to have, and truly in the circuit, you're going to have 3 distinct currents. One in this leg, one in this leg, and one in this leg. And I think I just sort of drew backwards depending on, but those 2 are essentially the same. There's no need for the 2 to mean anything. I'm just making up stuff. So this can be I1 and I2. That can be I1 and I3. It doesn't really matter. But there's 3 distinct currents in these 2 cases here, okay? And so let's just pick this one here for kicks. Why not? And so now, which equation would be valid for the top loop? So I picked that one. And let's just actually go, let's go through and just real quick do this signage here. So there's a few questions on the signage. Again, this is my method of doing it. And so when you pick your currents, and so I picked I3 to go this way. So the way that when the current goes through a resistor, it drops in potential. And so that's what this means. It's like the positive is the higher, the negative is the lower. So if my current's coming this way, it's positive, negative. These positive negatives for the resistors totally depend on how you define your current. If you had done your current the other way, those would switch. They have nothing to do with the battery, okay? They all have to do with just basically how you draw your current, all right? So the basic rule for that, again, with this method that I like to do is just that, okay, if I have, some resistor like this, like so, and I tell the current to be this way, then this is going to be positive, that's going to be negative. Again, when the current goes through a resistor, it's always a voltage drop. And so if I assume the current is going this way, then I draw it this way. So the current comes in at the positive, comes out the negative. So the current, the direction implies a voltage drop. All right? If you'd done the current the other way, you would switch those. And of course, if you get a negative answer, that means that what is the higher end of that resistor is different than what you thought it was. Okay? And so that's how I do those signs there. So I put the signs on there. And so which equation then would be correct for that top loop? So let's think about this and write this one out here. Okay, so it looks like most people have voted, and the good news is I agree with the majority. So let's just go ahead and mix things up. I'm going to start here and go this way with my loop, just to be as different as I possibly can be. Okay, so if I start here and go this way, I come to the positive sign first. So my first thing I'd write down would be positive 3 volts. Okay, so I get positive 3 volts. And so now I continue on, I come to here, so I write negative, Now, the current in that particular resistor is I1, and the resistance is 10 ohms. So I write that. Again, for that second one, the first sign I come to is that negative. So because of the direction I chose to go, okay, I'm going to get these sort of signs as my preferred sign then. All right, that's sort of the reason why we do this in the first place. So plus 12 volts here, and then negative I3 times 5 ohms, and I'm back to my point, and I say equal to 0. And if you compare with that equation, it turns out that that's the correct equation there. Again, sort of thinking about it, which I think, yeah, I mean, people were there already, but they're a little bit higher now too. So let's just stop. Questions on that? Because if you get everything we've done so far correct, then the rest is just algebra. Okay, you say just algebra. Yesterday it was not just algebra. That was nasty, right? But it's math at this point. So I really care about the physics. I'm not, that involved in how good your algebra is right now. But questions on how we got to this point here? Anybody got, yeah?
I wanted to know more about how we decide what branch will have what current. So you know how I1 becomes I3, and then the other branch becomes I2?
Yeah.
That gets a little harder for me in more complex circuits. So what's your thought process when you're deciding?
So it's just basically whenever there's a juncture, your current has to change. And that's literally all that there is, right? So basically that whole bottom part has to have the same current. The middle part has to have the same current. And the top has to have, so there has to be 3 currents here. And then basically you can make them go any way you want. Okay, and so this is the way I chose to make them go. You don't have to, but you can make them go any way you want. But anytime there's a juncture, the current has to change. And that's the easiest way to think about it. So start with the junctures. And if there's no juncture, the current has to be the same throughout that whole piece, right? Other questions? Now, if you remember, so the one we did in class, I did a video with the algebra. So you can go through and follow that one if you want. There's also, I think, one in the pre-class video for that day where I go through the algebra. So there's a couple different examples. But I thought, too, in this case, let's go through the algebra again. Okay? And so I get a loop here. So we got this first loop right here. And so what I'm going to do is I'm going to call this my equation 1. And here I can rewrite this equation 1 like this. So I'm going to actually do the algebra. So I get I3 times 5, and then that's going to equal 15 volts. That's 12 plus 3 minus I1 times 10. Okay? Now I'm doing something that you're never supposed to do, which is I'm dropping my units. I'm just doing it because my handwriting is so bad, so I'm just trying to compromise here. But if I take this equation here and condense it down, so I can write it as I3 times 5 equals 15 minus I1 times 10. And maybe we'll start this by kind of getting my next equation. So I think for my next equation, I did the bottom loop. And so I started right here, and I did the 10 right here and went around this way like so. Okay? And so if we do that, the equation I got was something like this. It was positive 10 times I1 minus 3 volts. That's the next one I come to. Plus 9 volts. And then minus I2 times 5 equals 0. So again, that's the loop for starting right here and going this way in the bottom loop. So I come to the positive for that guy, negative for that guy, positive for that guy, and negative for that one. Okay, so that's my method there. And so when I look at these two, and I'll call this equation 2, just to name it something. And so now I've got these two equations. They both involve I1. So my goal is to solve for the other current as a function of I1, which I'll plug in later to solve for I1. Okay, so that's why I went ahead and sort of wrote that one that way. And so the equation I get from equation 1, if I solve this here, I'll get I3, I just divide all sides by 5. So I get 3 volts minus 2 I1. So that's the equation I get from that first one. Again, my goal is to get I3 as a function of I1. If I take this one over here, again, I'm trying to get I2 as a function of I1. And so if I do this, I get I2 times 5, so I sort of swing that to the negative side of the equation, and then I'm left over with 6 volts plus 10 I1. So I'm left over with the difference between these two and then 10 I1. And then if I start with my equation 2 and solve for that I2, I get something kind of funky. I get 6/5. And actually, I should be real careful. That's no longer volts. So let's get rid of that. So I get 6/5 plus 2I1. So here I'm dividing both sides of the equation by 5. So divide by 5, divide by 5. So I get this 6/5, which is not fun, but oh well, and then plus 2I1. And so now my last equation, I'll do my junction equation. So I1 plus I2 equals I3. And this is usually you'll end up pulling this out. Usually it's faster to use this. And so here I'm just saying, like, for instance, at this point right here, my I1 and my I2 come together and my I3 leave. So I1 plus I2 equals I3. And so now we're done, or we're to the point where we can actually plug everything in. And so the I1 stays the same. For I2, I plug in this guy. And so it's plus 6/5 plus 2I1. So my I2 is now replaced with a function of I1. And my I3 would be 3 minus 2I1. And so if I clean this up, I've got 1, 2, 3 I1s over here. I'll bring this over. That gives me 5 I1 on that side. And over here, I get 3 minus 6/5. And if I want to be real slick, I can show that that's 9/5. And so when I solve for my I1 then, which is not going to let me to do here, so I1, when I solve for it, I got then 0.36 amps. Okay, and at this point, you're done. You just take these two equations. So if I plug in 0.36 for I3, okay, I got 2.28 amps. And if I plugged in this one over here for I2, I get 1.92 amps. So just plugging in this answer. So basically, the first one is usually the hardest. Once you get that one, you're set up to find the other two rather quickly, like that there. So questions on how I did this? So again, we'll have this. And so I've done at least 2 other examples with sort of algebra that's a little bit trickier like that, I think. So you can find those if you want more sort of, and definitely you just want to go through a couple of these to try it out. And so let's look here now. Let's just look a little bit more in depth to try to understand, maybe get some insight into more of this stuff. So here, what I've done is I just took the top loop and just copied it over, okay? Just because I want to understand it a little bit better. You do the same thing to the bottom loop, that's fine, but I just wanted to start with that one. And so let's look here. So we know that my big equation for the voltage across a resistor is IR. Okay, and I'll just write these over here. So the currents we got last time was 0.36A, and then for I2 and I3. So these are just copied over from the last page, 1.92A and 2.28A. And so if I want to find out my voltage, let's find out the voltage across the 10 ohm resistor. Okay, so that's this guy over here. That's current I1. So that would be I1 times 10 ohms. And so if I plug in 0.36 amps times 10 ohms, I get a voltage 3.6 volts. So my voltage for this guy is 3.6 volts. Okay? Now, my voltage across the 5 would be this top one over here. So the voltage for the 5, that's current I3. So that would be I3 times 5 ohms. And so I3 is, again, this 2.28 amps times 5 ohms. And when I did that, I got 11.4 volts. Okay, and so here we have all the different voltage drops for this circuit. And it worked out in this case that the way I guessed the currents worked out well. Okay, and so the thing is now, you know, if you think about this voltage loop law, what it's saying is that basically the voltage drops, if I go in a circle, have to end up being 0. And what that is I sort of made this analogy between that and like you're hiking. So imagine you're hiking somewhere. Okay, so here I start out and I go this way. Okay, so if I come this way, I'm entering in the positive side, and so I'm going down 3 volts. Okay, so if I start here and move over this way, I'm going down 3 volts. And so if I wanted to sort of write out my path, Okay, I would start out by saying, negative 3 volts that way. And then I come to here, and what do I get? I get negative 3.6 volts. Okay, so I started out, and so I go down 3 volts, and I'm sorry, here I'd be going up 3.6 volts. My apologies. Right, because why? Because, again, we think about these positives and negatives as being kind of going up, down. All right, and so if I start out here, I'm starting at the high end and the low end, so I decrease 3 volts. Here I'm starting the low end and going up 3.6 volts. I come over to here, I go down 12 volts. Okay, so negative 12 volts. And then I come to this point and I go up 11.4 volts. And if you add up all of these, it adds up to 0 volts. And it won't always be so nice. Sometimes there'll be little rounding errors, but this actually worked out well. But that's the idea, okay? The idea is that, if I go hiking and I come back to the same point, the amount that I hiked up should exactly equal the amount that I hiked down. So this is the kind of picture that if we ask questions like, what's the voltage drop across this resistor, you'd want to picture it kind of like this. Okay, I'll be down here if you got more questions about this.